Okay, this is about divide and conquer. We'll be covering the concept of divide and conquer as well as with it recursion. Just get my notes up on it. Good. So first off, we'll be going over the concept of tiling a grid. So if we have a grid such as this, which is some value of 2, yellow, 2 to the power of n. That's important because it has to be some power of 2. So we have some grid that is 2 to the power of n wide and tall. It's a square. On it, there is a single filled-in piece, and we are trying to fill it using a triamino, which think of tetrameter for Tetris, but rather than 4, we have 3. Specifically, this triamino is of R shape. So we are trying to tile this entire grid where there will be no white spaces left using this shape in various positions. We can rotate it. So this would be a fine shape, but so would this. And we need to do the entire thing. And we know it's possible because, or we know it's not impossible because there are a multiple 3 number of white spaces. So the first way thing to do when approaching this problem is to divide it down into its unit case. We are trying to find the smallest possible version this could be, where we can then build up. That's the whole concept behind divide and conquer, is find the unit case, the lowest possible value, from which then you can try reduce the problem to. And that is this scenario. That was not what I wanted to grab. This scenario. And in fact, this scenario. Again, not what I wanted to grab. And all the other rotations thereof, where you have bottom left and top left. So this 2x2, because you can see, you fill this in, you fill this in, you fill this in, you've got your shape, and you've got a filled-in square. So we can find a way to reduce this grid, which is 8x8, to a sequence of 2x2s, then we've solved the problem. Because if we can fill every single one and ensure every single one has a filled-in piece already, then we are good. The idea behind this is we divide the problem down, hence divide and conquer. This is the conquer part, there is to divide it. And the idea is, for this problem, let's make this a bit bigger. You go down like this, and you go down like this. Actually, this section has a missing piece, so there is still a chance that we could do it. These sections, though, don't. They have one extra thing, so we could never possibly do it. So where do we want to put our block? We want to put it here, here, and here, in that orientation. Now, these are possible again, because they have a multiple 3 number of spaces. And from there, we can then further subdivide down. So if we just go into one of them, for example, we can go into this path. This path has now been subdivided down again. And again, we want to put our piece where in the 3 quadrants where the current one is not. So that's this one, and this one. And now we have our unit cases. Here you can clearly see putting one here, one here, one here, you filled it. Same goes for this, same goes for this. And this process can be repeated for this section, and this section. So we've finished the problem. We have developed a solution which can solve the problem by dividing it into pieces and then conquering it as you build the solution back up. Because you would then do this, you do this, and then do this, and this quadrant done. Then you repeat that process for this quadrant, this quadrant, this quadrant, and the entire thing's done. If you have another one of these, which was if you increase the n by 1, you'd have another lot of this like this, another 4 quadrants. This would be 1 quadrant in that problem. That's the concept behind divide and conquer. And the word for that is recursion. Let's not have blocky letters. This method of finding a solution and then repeatedly using that solution on ever small tightening in what's the word I'm looking for? Data. So we take our scenario, we divide it up into smaller and smaller bits, which are ever getting closer to our unit case. And our unit case are how we break it apart. If you're trying to define this, then if you didn't have these unit cases, you'd recurse all the way down to 1 by 1, and then you wouldn't have a solution. So you always have to identify your unit case and then try and find your way to that unit case. Another example is array summation. If we have this array of numbers and we want to find the sum of all of them, one way would be a linear traversal. You go 1 by 1 in a for loop and take the thing, add it to a variable that you're storing in, take it, add it in, add it in, add it in, add it in, all the way through, and then you have your total. Another way is to divide it and conquer it. What is the unit case for this? Well, it is two numbers, because addition takes 2 operands. So we want to divide this into units of 2. And for simplicity, we are presuming that, again, this is sum n to the 2 to the n. Though it can very trivially be expanded further. I'll get to that at the end. Well, at the end of this section. So for that, you just want to split it in 2. So you want this. You have this subarray and this subarray. And then for that one, you want this and this. And suddenly you have 4, 6, and 3, 2. And you can add 4 and 6, and you can add 3 and 2. So you then put that back up. So that's 10. And then that's 5. So there it's 10 and 5. So this bit sums to 10 and 5. That's 15. And then this bit the same. Break it up. Break it up. 5, 6. This is 15. And that is 21. And 15 at 21, again, can be done in a single step. And that's the same complexity as doing the linear method of breaking the problem down. Our unit case here would be having just 2 in the array. Array of length 2, that's when you're done. However, if you had an array which wasn't according to this pattern, then you wouldn't necessarily be certain you can have that. You could potentially have an array such as this. If you've done the dividing, now you've got to a stage where you have a 7, 5, 1. Say we took out 8 from this. So you have 7, 5, 1. How do we split this? Well, how you do it is you put a break here, add these normally, and then have a separate unit case for an array of length 1. And then you just return that and then sub these two. So rather than have one unit case, which is an array of length 1, you have a second unit case, array of length 2, a second unit case of array length 1. In either cases, you either return the sum or return the value itself. And that will then work for any length list. I think it should. At the end, if people wish it, I can jump in Python and try and code up a quick solution to this and to this. No promises it will work, but I can try. I don't have the pseudocode memorized, so I'd have to figure out off the top of my head. Okay, so this is one of the best sorts there is, merge sort. And the idea again is divide and conquer. We have some array, and we're trying to sort it from descending to ascending. And we can do bubble sort, we can do insertion sort, we could do a selection sort. But using a divide and conquer method, rather than going through it left to right, we can split it up and divide it down. Because a merge sort, its base operation is comparison. And for comparison, that again, like addition, takes 2 operands, A and B. So we can split this down to units of 2, or units of 1, because a 1 number on its own isn't greater or equal to anything, you just return it itself. Then you can sort the entire array, because it's much easier to sort 2 semi-sorted arrays, 2 sorted arrays, than to merge 2 unsorted arrays. If you have 1, 7, and then another array which is 2, 4. If you want to merge these arrays, well, you know for a fact that the smallest element of the new array is going to be either this one or this one. So you have to compare them. You go through, compare them. Okay, 1 is smaller than 2, so we put 1 in. Going through, we have a 7. Is this the next one? Well, 7 compared to 2. No, 2 is next. Next one is 4 less than 7. Yes, it is. Put 4 in. 7. That's a much faster much faster merging while maintaining sorting than if you had two unsorted lists. If this was 7, 1, and then 2, 4, you wouldn't know anything, so you'd have to do an entire sorting algorithm. So using this method, you can have a much faster potential merging of these arrays. So again, you want to break it apart down the middle. Again, break it down apart in the middle until you have those unit cases of 2, and you have to compare. So this case is an array of 51, 13, 10, 60, 64. This one is 34, 5, 32, 21. Split it again. You have an array of 51, 13, and then another array of 10, 64. Here you have 34, 5, 32, 21. And now you have your unit cases. Here are your unit cases. 51. That's a terrible looking 3. Wrong color. 13. There. So here's your unit cases. So now you have to compare them, and if needed, swap them, otherwise just return the array. So 51, 13, that's the wrong way around. So what we want to do is return 13, 51. And this one, that's the right way around. So just 10, 64. That's again a 4, not a 6. This one we have 5, 34. And 21, 32. That's a terrible 2. So now we have 4 arrays, all of which are sorted. Now we want to merge them. We want to merge this array and this array. And again, if we look at the first position in both, like so, we want to find which of the... Oh, we want to look at this one and say, is it smaller than this one? No, it's not. That means we have to put 10 in. And we keep looking at this one because we haven't found anything yet. So we look at the next one in the array, which is 64. 64 greater than 13, so we put 13 in. And we look at this one again. We move this pointer further along, now looking at 51, and we again look at the pointer for the second array, do the comparison. 51 has to go in first, then 64. Much faster, again, than what we could do if they were unsorted, because we can make the assumption that as you go further, you're going to get bigger and bigger numbers. And again, for this side, I'll put these in. For this side, we're going to make another array. Same thing, 5 and 21, put 5 in, 5 and 34 and 21, put 21 in, 34 and 32, that's 32 and 34. And then once again, you have to do the comparison of the two arrays. 10 and 5, that's 5. Then we have 10 and 21, that's 10. 13 and 21, that's 13. 51 and 21, that's 21. 51 and 32, 32. 51, 34, 34. 51, this is empty. Oh, we're at the end now, so we just put them in as they are. No comparison required. And there we go. A sorted array in what is actually one of the best times in sorting algorithms. If you work out the complexity of this, it is O of n log n. Compare that to selection sort, insertion sort, bubble sort, which are all O of n squared. This is much, much, much better than that. No longer being polynomial and going instead into this is so much better, and merge is one of the best sorts that there is. And this shows the power of divide and conquer. Was there anything else I had to cover on this? Double check my notes. Oh, yes, there is also the point of recurrence, which goes into this. Now, recurrence, I'm not going to put a section on, but it is the notion of finding the time complexity of recursive algorithms. Because they don't have for loops, you can't just analyze how many times it will go over for every single one. So instead, you need to do some mathematical hokey pokery, which we don't need to know for the exam. You need to know it, but because these variation tests are specifically for the exam, I'm not going to be going over it. It will be tested and examined in the next lot of this series of modules in semester 1 of next year, I believe. I forget which module, it might be semester 2. One of the two. We'll use it then. But this is the concept of recurrence. Recurrence because these are recursive algorithms, they call themselves. And that is it. So unless people are interested in me coding up this and this, that is everything. Either Jeremy, you can mute on, but keep in mind this is recorded, so you may want to just type it. Up to you. The grids, the tiling. Left corner on. What did I say? Oh, I said they were. Oh yeah, technically these were the same. The fact that they're different doesn't matter so much as the fact that they are all following they are one of the 4 unit cases. That's the important aspect. I think I might have misspoke. The differentiation between them doesn't matter so much so long as they fall into the category of one of our 4 defined unit cases of having a 2x2, one of which has a filled in square. Okay. If that's it for questions, then we are done.